in this talk, I will touch on a few different topics where we will see how to, or at least make some effort towards finding analysis tools for optimization algorithms that provide bounds that are close to what happens in practice, and also how to use this to design faster optimization algorithms in general. So let me start with the applications that I'm actually interested in my work. So there's many areas, for example, from logistics to energy, but also robotics, transportation, where we rely on a very dynamic and fast-changing environment. For example, in energy production and distribution, you may have extreme weather events that significantly change the way that we need to operate the grid. If you're controlling a fast dynamic assistant like a robot, you may have unseen obstacles that affect your operations, but also in logistics, you may have the supply chain being drastically disrupted by various different factors, from human to also weather-related behavior. So in all these situations, in order to operate the system, we need to make fast and effective decisions in real time. And optimization is a very useful tool to do that, because it allows us to plan and adjust our plans on the fly by just solving optimization problems with an accurate representation of what's going on in these applications. For example, if there's a disruption in a road network for public transportation, you may, in order to react to it, since you're in a re-optimization setting, you may just block the road or add constraints that force you not to use that road. And this flexibility is very important, because if you're able to solve these problems, in real time, we can make our systems more resilient. Now, which problems am I talking about in this talk? These are parametric convex optimization problems, where we will use first-order methods to solve them. So let me jump right to the problem class. So I'm interested in solving problems where we want to minimize a convex objective function of our decision variable z, subject to z living in a set of constraints c of x, where x are the parameters that affects our problem. So you can imagine that x follows an unknown distribution, and every time you sample from this distribution, you sample a realization of x, and this realization gives you an instance of the problem that you want to solve. So for example, x could be the state of your dynamic system if it's an optimal control problem, or the loads and the state of charge across the units in your power distribution network. And then these parameters, once you see them, you need to solve the problem and compute the optimal decision z. So in the algorithms that we will use to solve convex problems of this type are first-order methods. So for example, a common way to solve this is using projected gradient descent, where we compute a gradient step. At every iteration, we compute a gradient step of the function f with respect to the first decision variable zk, and then we project onto the set of constraints c of x. Okay, so that's just an example. There's many, many variations and different algorithms you could apply to solve these problems with first-order methods. And these algorithms have been around for a while. It's not the first time we work with these algorithms. Actually, from the 60s, they were developed and even earlier. But I would say we've seen a resurgence of these methods for two main reasons lately. One is that the iterations are very cheap, which means they can be deployed. You can solve huge scale problems on a supercomputing cluster. And this is probably what most people are familiar with large-scale optimization tasks, for example, training deep networks. But also on the other end of the spectrum, you can deploy these algorithms on very light, small computational platforms like embedded systems, for example, microcontroller devices. So this flexibility allows you to really go to extreme small or large scales. And also, and this is because you have cheap iterations. Now, the other reason is that you can also warm start these algorithms, as opposed to, for example, interior point methods that cannot be easily warm started. But for pseudo-methods, since we're solving many problems that are related to each other from these parameters x that we observe, then being able to warm start the algorithms from the previous solution is a very important feature that allows us to possibly require fewer iterations. And given these benefits, we've seen a recent explosion of many different available solvers, from linear programming to quadratic programming, and even second-order cone or conic problems in general. There's even a big interest nowadays. NVIDIA just released an open source GPU-based solver co-opt that is actually a suite of algorithms to solve optimization problems, mainly using first-order methods on GPUs. So there's definitely lots of interest. And these methods are way more reliable than what they used to be in the past. However, they are not always working as what we expect. So actually, they may converge slowly in many different situations. And if you work with them, you know that you may often be able to construct an instance for which they do not converge as fast as you wish, so that they require many iterations, which is a problem if you're working in real-time systems where you want to compute decisions fast and within strict real-time requirements. For example, in a power system, you need to solve these problems within a few minutes. In a mechanical system or a robot, you need to solve these problems in milliseconds. So these are hard deadlines that we need to be able to satisfy very reliably. And also, the other reason is that on many of these systems, you have a limited computing power. You cannot just add more compute to make these algorithms faster. This doesn't work for many of these applications. So this is the bad news. However, the good news is that in many of these problems, you don't really solve one instance and go home. Actually, you solve many related instances from what I was saying before, where the structure is the same. So the only thing that varies between one instance and the other are these parameters x, which means that the structure of the problem is the same. For example, the layout of your power grid doesn't change between one instance and the other that you solve, or the dynamics that operate your robot do not change between one instance and the other, which means that we collect lots of useful information by solving these problems in two different ways. One is that we collect large amount of data we collect how these instances are distributed, the solutions, how long it takes to solve these problems, but also we collect lots of useful information that map the parameters x to the solutions of all of these convex problems that we generate by varying x. So in this talk, I will try to use these two important features, so the structure and also the data that we generate, in order to analyze and design hopefully faster first-order methods, in order to be able to deploy them reliably in these applications in real time. So in the first part of the talk, I will focus on verification, which is the problem of analyzing these first-order methods, and I will analyze them both in the worst-case sense, where we want to always be 100% sure that we never violate some conditions on the quality of the solutions, and then in the probabilistic sense, where we may allow sometimes, rarely, to violate these constraints, but we want to control how often it happens. And then in the second part of the talk, I will work towards designing first-order methods and try to use this data to learn faster variance by adjusting some hyperparameters and still ensure the guarantees, the probabilistic guarantees that these methods work very often, actually very rarely they fail to provide good quality solution. So let me start from the first part, verification. So before jumping into verification, we need to understand what does it mean to analyze the convergence of these methods. This has been done for decades, so I'm just gonna talk about one way to do it. So we can think about first-order methods as operators that map a iterate zk to the next iterate zk plus 1. And these operators have some properties, could be contractive, averaged, and under suitable assumptions, they converge to fixed points, which are the points for which if you apply the operator one more time, you still keep the same points. And these are the goal of what we want to find with all these methods. And remember, we're solving convex optimization problems that are parameterized by x, which means in the very simple case, let's say that I want to solve an unconstrained problem using gradient descent. Just for simplicity, we can, the problem is minimize f of z comma x, given x. So the optimality conditions are simply that the gradient at z star is equal to 0, right? And this can be, and the way to solve this problem using gradient descent is to apply iteration of the type where we take zk, we take a step in the negative gradient direction, and then we get zk plus 1. The fixed points here are the points at the bottom here, where I have z star is equal to z star minus the gradient. And if you cancel out z star, this exactly corresponds to the optimality condition that we want to ensure. So, and this is not by chance, actually, all these methods, even when you have constraints, the fixed point condition correspond to the optimality conditions of this problem. So the goal is to really go as close as possible to these fixed points. And a reasonable performance metric to understand how well we're doing is to look at the fixed point residual, which is a difference of the last two iterates. If you go to a fixed point, the last two iterates will become the same. So this vector will become 0 and the norm will also become 0. And we will call this performance metric R for residual, K after K iterations, and X that depends on the instance X that we're solving at this point. Okay, so this is what we will use to judge these algorithms. So this is there's lots of literature on analyzing first-order methods, and in particular, there has been the best known bounds now are given by numerical methods to actually estimate the performance of these schemes. And they work as follows. I'll give you just a one slide overview of this literature on performance estimation, which is closely related to what we are doing. So this literature doesn't use parameters x, so the function and the operators are not represented by x, but the idea of this method is to formulate an optimization problem to analyze these schemes. And the optimization problem works by maximizing the performance metric, which means you want to find the worst case, that can happen in terms of performance metric. And then you want to be within a function class. And the function class is, for example, all the strongly convex and smooth functions. And these are the typical assumptions that you do when you teach optimization. You say that I have all the functions that are strongly convex, smooth, or that are just smooth. And you want to translate this condition as well as the iterate z0 to zk belonging to the algorithm t applied to f into tractable constraints of this problem. And to do that, there's a beautiful theory on using this interpolation condition that allows you to represent the functions, which are in an infinite dimensional space, just at the interpolated points, which are represented by this iterate z0 to zk. And I'm not going to go into the details because it's not exactly what we are doing here. But the main point is that this allows you to write a finite dimensional problem. And also, if you set up an initial condition, for example, the initial distance of the two iterates is bounded by R, then you can get a finite dimensional representation. And then the performance estimation literature allows you to go even beyond the finite dimensional representation and get a convex formulation of this performance estimation problem, where it becomes just a semi-definite program in terms of this gram matrix G, where G are just the norm of the difference of the iterates or the gradients that appear in your algorithm as the iterates progress. So there's lots of literature on this. The nice thing is that this SDP is independent from the iterate dimensions. And it's just a convex problem that gives you tight bounds, and it has been used to study lots of these schemes lately. Now, these best known bounds, however, may be very pessimistic for some for the setting that we're considering. And let me give you an example of how these bounds can be pessimistic. So let me generate a distribution of problems synthetically by taking all the images of letters in the EMNIS dataset and blurring them, and then formulating a problem of deblurring these images by trying to construct a deblurred image from the blurred image by solving this nice convex quadratic optimization problem, where Z is the reconstructed deblurred image that we want to find, is between 0 and 1 because it's black and white pixels, and then it depends on this blurred image. Every time we observe the blurred image, we need to resolve this problem here. And if you solve this problem, in general, I get this behavior here. I get the convergence criterion on the y-axis, and then on the x-axis I have the iterations that happen. And then you could see that the brown line is the theoretical worst-case bound that I obtained using the theory before. that I talked about in the previous slide. And then the black line is the sample average, which is across this distribution of instances. I take the average behavior of my convergence criteria, which, as I talked about, could be the fixed point residual. And then I take, so the average behavior is still way better than the worst case behavior. That's expected. But what's not really expected is that the 99th quantile, which is literally almost the upper bound on the worst case, true worst case behavior in practical sense, it's this purple line, which is way below the worst case line that we obtained from the theory. So the worst case bounds are way more pessimistic than what actually happens in the worst case by looking at a specific distribution of problem instances. And what does this happen? So there's different reasons. So the first reason is that we're looking at a much more restricted function class. I mean, in general, the ones assumed by known bounds are, for example, strongly convex and smooth, which means that it's way more generic than the function class obtained by just parametrizing the problem with this in a specific way, which means we may never encounter the worst case function, but also we may never start from the worst case initial point. This may just happen in terms of the you may just start from a point that is much closer to the optimal solution, especially if you're warm starting your algorithm, if you solve this problem in real time, which means that in practice, we actually have just a distribution of instances that is much more structured, for which we would like to understand more what happens and be more specific. So to do that, we take a different approach. We try to represent algorithms as this fixed length computational graph, where we look at the inputs, which is this problem instance, and the output, which is this the iterate after k iterations. And then what happens inside is that you construct an initial point z0, either by warm starting or even cold starting at 0. And then we apply k iterations of your operator t in order to get the iterate zk. And then these operations, so the warm starting and the operator, will rely on some hyperparameters that are based on step sizes or acceleration warm start. So there's many different things that you can tune for these algorithms, but we will not tune them for the beginning of this talk. But these algorithms, if we look at the difference, how the input affects the output, they allow you to understand a much closer relationship to what happens in practice. Because for example, if you apply projected gradient descent here, you may start asking the question of what happens if you change the problem instance to the output, and how can we find the worst case realizations of these instances that degrade the performance as much as possible of the outputs in order to analyze this method. So it's a similar question as a performance estimation, but we have a much more structured problem. So what happens here is that if we look at the algorithms in this way, then we can ask two interesting questions. So the first one is what happens to the fixed point residual in the worst case? So if you have a set of instances that is X that lives in a set calligraphic X, then we may ask the question of what's the largest norm of the residual that I can achieve by changing the instances within the set of instances that I'm working with. And this is a worst case approach. So if we can if we can solve this problem of maximizing Rk, and then the worst case value is less than epsilon, then it means that my algorithm will always return solutions of tolerance less than a given epsilon that I'm happy with, for example, 10 to the minus 3. Another approach is the also probabilistic approach, where you can also look not at the worst case, but at bounding how often it happens that I violate these conditions. And this could be the problem of if you have a distribution of instances, you want to bound the probability of failure. And this is the probabilistic approach that has also an important meaning if you allow your method to violate the constraints once in a while. So let me look at the worst case approach first. So the worst case approach can be formulated if we can add more structure to the problem. So in this case, in the work that we did, we looked at a parametric quadratic optimization problem just to add more structure and understand what happens in this case. So these are problems where you have a convex objective function, and then the parameters enters in the linear part of the objective or the right-hand side of the constraints. We can represent also a linear problem if we set p equal to 0. And we can apply all your favorite method could be ADMM, primal dual hybrid gradient, or even projected gradient descent, whatever you want. And we would like to analyze how these methods behave. And again, as I mentioned, theta are the parameters of the algorithms, or we consider them the hyperparameters, and we consider them fixed for the analysis purpose. So then we can ask the question of trying to analyze these algorithms by formulating this maximization problem over the fixed point residual as follows. So we can maximize over, by finding the worst case problem instance, the fixed point residual, which in this case is set as the infinity norm of the difference between the last two iterates. And then I can apply my first of the methods from one iteration to the other until iteration k. And I use infinity norm here for two reasons. One is that it's used in most, I would say, general purpose solvers. The actual termination criterion is the infinity norm because you want every component of your residual to be less than a tolerance. And also, I'm not going to talk about the set z theta x or z theta or x calligraphic x because you can imagine them as being polyhedral, these two sets here. But the interesting thing are actually these iterations from zk to zk plus 1 that are difficult constraints to model in this problem. And actually, we show that this is a NP-hard problem. It's not surprising that is an NP-hard problem, but we showed it in this paper, where if you maximize the norm, which is already non-convex, and you have these constraints, there's only in very simple cases, it's possible to solve it in polynomial time. So instead of then looking at relaxations, what I would like to talk about is how to construct tight formulations of this problem. And in particular, I would like to construct exact representation of these algorithms as mixed integer linear constraints. And I'm going to do it by representing all sorts of algorithms that you can apply in these scenarios as two types of steps. So the first steps are the easy ones, which correspond to linear constraints of the problems. These are steps that are represented as this matrix n that multiplies zk plus 1 equal to azk plus bx. So this can represent gradient steps because we're looking at parametric quadratic problems. So gradient becomes just a linear step. Then momentum accelerations, restarts where you average the iterates, anchor steps, but also proximal operator or quadratic function. These are all linear steps that we can add into the verification problem in the previous slide very easily. The difficult steps are the piecewise-affine steps where they correspond to mixed integer constraints. For example, if you have a one-sided projection on the non-negative order, then this becomes the maximum between all the components of z and 0, which is just a ReLU function that we can apply. So it looks exactly like a ReLU function that you see in neural networks. But also other steps could be interesting. The soft thresholding operator is just a proximal operator of the one norm function that just becomes this piecewise linear function here that can also be represented with mixed integer linear constraints. And even if you do box projection, they correspond to this other operator, the saturated linear unit, which is literally just doing the clipping up and down of every component of the variables. So all of these can be represented with mixed integer linear constraints. And if you have, for example, a non-negative least squares problem that you want to solve, here on the right, we can apply projected gradient descent, where you do a gradient step in the objective and a projection onto the non-negative order. The first step is a linear step, and the second step is a projection step. So there's all these algorithms that can be represented in this way. And then if you work with neural network verification, you may realize that there's a strong connection between this type of algorithms and the algorithms in neural net or the formulations of neural network verification. And there is indeed a strong connection. But you also know, if you work with this in these settings, that it's hard to solve this problem. So in the next slide, I would like to talk about how to actually go and solve these problems at scale to actually analyze some of these constraints. So the first part is to construct tight, strong formulations. For example, if you look at the soft thresholding operator in high dimensions, it looks like this function here. And in order to solve these mixed integer problems at scale, we would like to construct formulations that closely approximate the convex hull as much as possible. And we were able to extend formulations from neural network verification to these problems of verifying first order methods. And we were able to show that the convex hull formulation can be written by generating these kind of plots, and it requires an exponential number of inequalities. That's not surprising. What's nice though is that it can be the problem of separating this object is actually solvable in linear time. This doesn't mean that the overall verification problem can be solved in linear time, because there's other parts that are non-convex, but this allows us to construct tighter representations of all these steps that I talk about here. The second improvement that we worked on that actually allowed us to really scale this method is to use operator theory to tighten these formulations. And the operator theory helped us in the following way. So remember, the objective of this verification problem is this performance metric in red. If you know how the algorithm behaves, you know, for example, from operator theory, that if you have linear convergence, this difference can be bounded by constant alpha k, which decays geometrically, okay, at rate tau. If we use this information combined with previous bounds on the continuous variables of our problem, which is, for example, the iterate at k minus 1 iteration, and the lower bounds are the underbar and bar iterates z underbar is z over bar. We could combine this information by doing a very simple, obvious implication that says that if this what's on the left holds, then we already know bounds on zk by just subtracting and adding this alpha k to every element of the lower and the upper bound respectively. So what does this mean? It means that we can actually solve this verification problem for an increasing number of steps by just solving it at iteration zk minus 1, then verifying the performance, then computing the bounds at zk for the iterate zk, and then verifying for zk, and continuing until we get to the value of the number of iterations that we're interested in. For example, the ones that our budget of computations allows us to use. So these two ideas of constructing some formulations and using this iterate solved by combining operator theory allows us to really scale this problem. So let me just show you one example. This is a sparse coding problem for signal reconstruction. You want to, every time you observe a noisy signal and you have a dictionary D we want to use to represent the signal in the sparsest possible way by reconstructing this vector Z. And we have the L1 norm to induce sparsity in this problem. It's a typical lasso-like expression. And there's many algorithms. The typical one is the iterative soft thresholding algorithm, where we do a gradient step in the quadratic smooth part of the objective and a soft thresholding operator to deal with the one norm. There's also faster versions where we have momentum. For example, the fast iterative soft thresholding algorithm, FISTA, adds a momentum step to these iterations. And if you want to observe how this algorithm behave with this verification formulation that I told you, we obtain this kind of behavior. So here I plot the behavior for strongly convex functions and for on the top and convex functions at the bottom. The green line is the theoretical best known bound using the performance estimation problem formulation using an SDP. The red line is literally, if you sample many instances, we take the worst case. And the blue line is actually the solution of our verification problem, which is much tighter compared to the actual sample maximum. It captures much more the actual behavior you obtain per iterations. And also, it exactly captures the ripples that you obtain in momentum-based algorithms like FISTA, which is very interesting to see because the other techniques to estimate the behavior of these methods cannot capture that. Also, in terms of computation times, we do take longer than non-SDP approaches. So I'm just comparing the two times here. In blue is our method, and you can see that it does take longer because we solve a mixed integer linear program, but it's reasonable until these, let's say, 4 iterations, which is something that we weren't even expecting before. If you compare it to neural network verification, where people verify neural networks of just 5 layers, doing 40 steps, where here steps are the parallel to layers in neural network verification, these are way more. And this is thanks to the operator theory bounds, and which here I'm just showing you how they help. So here I have on the y-axis the fractional components. that are tightened using the operator theory bound, and on the x-axis have the number of iterations. And you can see that for the strongly convex problem, I do have linear convergence. So the operator theory will tighten way more components for both East and Vista much more quickly, which means that tightening the components is a very good procedure to accelerate the solution of these mixed integer linear problems. For convex problems, we do not have linear convergence, so the operator theory will help us less, but still it's very efficient, and we're allowed to solve problems up to 40, 50 iterations, and you can still get some help in the last part of the iterations of this scheme. Okay, so this is the part about worst case analysis. Now I would like to talk about the probabilistic analysis to understand what happens if we allow to violate the tolerance a few times. So the probabilistic analysis works as follows. We want to use, since we're looking at probabilities, then we could use tools from statistical learning theory to help us understand how often bad quality solutions happen. And statistical learning theory allows us to start by, instead of representing this probability, we can represent the expectation of an error function, which is a 0-1 error function that tells us whether or not our method solves the problem up to epsilon accuracy. And there's a nice parallel between statistical learning theory and our problem in optimization. So in statistical learning, we want to classify an image. So the input is an image. In our case, the input is an instance with parameter x, for example, an image of a cat. Then the hypothesis is that the cat, we either have cat or not, and in our case is the residual after k iterations of when you start from parameter x. Then we have an error in classification, whether or not we classify the image correctly, and in our case the error is whether or not the residual is above or below the threshold. And the guarantees that we want to obtain are the expected loss on new data for classification, and in our case the expected loss on new problem instances. So there's a really strong parallel between algorithms and predictors in machine learning. So how do you estimate the loss on new problem instances? So to do that, we can do a very naive approach where we actually allow ourselves to run the algorithms a few times, right? There's no need to do the entire analysis without running the algorithm a single time. So we could just take k steps of the algorithm and take n instances that we sample from our distribution and compute all the candidate solutions for every instance. And then we can compute the empirical risk, which is the average error, which tells you how often I failed in my data set of instances. And then we could use that to bound the true risk, which is the true probability of failure over this distribution of problems by using bounds from statistical learning theory. This is a very simple approach, but the nice thing is that it can give you very tight results in optimization. So for example, this is one of the bounds you can construct. This is from Langford, this is from almost 25 years ago, and it tells you that with probability 1 minus delta, the true probability of failure, which is the blue risk here, is bounded by what's on the right. And what's on the right is the inverse of the KL divergence between the true risk and the empirical risk. And then so this is a 1D convex optimization problem. And then here I have the empirical risk, which is exactly how often I fail over the data that I observe. And then I have a regularizer that depends on the number of instances that I've observed, and delta, which is the confidence that I want to obtain. So a bound like this, if the right-hand side is equal to a constant b, a bound like this tells you that with probability 1 minus delta, the fixed point residual is above epsilon after k steps, b fraction of times. Okay, which is very important because it tells you how often you violate the tolerance that you're happy with. And you can estimate it directly by just running the algorithm on a few instances. So let me go back to the image deblurring example I told you before. So if I take this method and I solve it with an algorithm similar to the USQP solver, then I can plot the fraction of problems solved and obtain bounds of this type. So on the y-axis is the fraction of problems solved. Here I plot with tolerance 0.1, 0.01, and 0.001. And you could see that here I have the number of iterations. The black line is the sample behavior, which is the fraction of problems solved that I obtain by just over samples. The brown line is the theoretical worst case bound, which is the one from the theory that I showed you before, which just goes from 0 to 100% because it's a worst case type of behavior. And it's very pessimistic, right? It tells you that you require, let's say in the higher precision version, 100,000 samples almost to solve the problem to 10 to the minus 3 precision. But our bounds, for example, if you have just 10 samples, this is the red line, which slightly improves. Of course, 10 instances as to understand the behavior is not enough, but you can also apply 100 samples in blue and 1,000 samples, which means you solve 1,000 of these problems offline, and then you can observe, you can tightly bound the behavior very closely to the empirical version, which means that we can exactly quantify the number of iterations required to solve all the problem instances using the green line here. And we can do it with high confidence. And the important thing is that these red lines that I showed here are way lower than the number of iterations required if you just apply the known worst case bounds, which do not observe how the method behaves. So, and again, this is just one of the bounds. There's many more than one could apply to analyze these schemes. So in the last part of the talk, I would like to briefly talk about how to use these tools to verify the behavior of these algorithms, and in particular, the probabilistic one, to design faster methods. And in particular, design, what do I mean by design? So if you go back to the computational graph, where we map the problem instance X to the iterates decay, nobody prevents us from plugging these iterates into a loss and then updating the algorithm hyperparameters like step sizes, accelerations, and warm start in order to improve our loss. We're effectively learning to optimize in this way. And this has been done for a while. There's so much literature on this, both for discrete and continuous optimization. What hasn't appeared so much is the idea of constructing guarantees for these methods. And this hasn't been applied much because most of the literature focuses on getting very strong performance, but without bounding the guarantees. But since we're working with statistical learning theory, there's beautiful tools available that we could apply to build tighter bounds and also bound the performance of these learned optimizers for unseen problem instances. So let me give you a 2 slides overview of how PAC-Bayes bounds work, which are the ones that we will use here. PAC-Bayes theory works with randomized predictors where we want to minimize the risk, where instead of having only the expectation over X, we also have the expectation over theta, which are the hyperparameters of our algorithm that follow a certain distribution. You could imagine a sequence of optimal step sizes, and then you have a Gaussian distribution around that sequence, which works as a mean, for example. And it is to find the optimal distribution of these methods here. And to do that, we follow 4 steps in PAC-Bayes learning. The first one is to pick a prior before observing data of the distribution of your algorithm parameters. It could be the theoretically optimal one that we know from analyzing these methods a priori. Then we observe the data, which means you observe many of these instances. And we then learn a posterior, which is the actual distribution of hyperparameters that we would like to use here. And the nice thing of PAC-Bayes theory is that both the prior and the posterior do not need to be consistent with the true prior of your data, which means that compared to Gaussian processes where you have to have a Gaussian, here there can be anything. Of course, if you choose bad prior, you get bad performance, but they're still valid bounds. And the bounds on the performance are the ones you construct here, where this is the confidence, with confidence 1 minus delta over draws of n samples, you can bound the objective of your learning task by this quantity t hat n, where t hat n is the data-driven bound that is very similar to the one I showed you a few slides before. But the difference here is that we're learning the step sizes, so we cannot use the bounds, the concentration bounds that we had before. We need to use generalization bounds of this type, where here I still have the KL divergence of the empirical risk here, where we also have the expectation over the actual distribution of theta. And here the regularizer is what changes, so we have not only something that depends on the confidence and the samples with the logarithm and the confidence n and the confidence delta, but also we have the KL divergence between 2 distributions, which are in this case 2 Gaussians, between the prior distribution of your parameters and the posterior distribution of your parameters. So you could imagine this working as a regularization term that helps you not go too far from the prior distribution and overfit your data. You want to have a balance here. So these ones have been around for a while, but the really powerful thing that happened not so long ago by many of the papers that I mentioned before is that these bounds started to become quite tight through some smart adaptation of these schemes. And in particular, one of the smart ideas was to directly minimize the bounds using stochastic gradient descent. So instead of minimizing just the risk, we minimize the bound directly. And we can do it by making all these expressions in this objective differentiable. So the KL inverse is a convex optimization problem where we can differentiate through. The empirical risk can also be made smooth, and also the regularizer. So we can make everything differentiable and minimize directly this upper bound using stochastic gradient methods. And what do we obtain after these schemes? We obtain a distribution over the algorithm parameters, which is, for example, a Gaussian where mu is the optimal sequence of step sizes from iteration 1 to k. And then we have a variance lambda, which is just the variance of the distribution that we can pick that is obtained directly from these minimization schemes. And then we have also numerical performance bounds that is the value of the objective after the stochastic gradient procedure that gives you a tight representation of the worst case behavior of these schemes. And the very interesting thing here is that we can directly use these bounds and get a sense of what happens for unseen samples. So let me go back now to show you just one example of how this works in the interest of time. So this is a signal reconstruction example where this is similar as before, where we have a noisy signal, we have a known dictionary, and we want to reconstruct a sparse representation of this signal. And here we have the performance metric, which is a normalized mean squared error between the iterate z and the ground truth. So this is something that we can do over synthetic data. And this is, however, a very good indication if this method works. And it works in decibel here. This is a normal metric used in these schemes. And then we can apply all sorts of algorithms to solve this problem. We will compare ISTA, which is the one we talked about before, where we apply gradient step and a soft thresholding operator. And then a learned variance, which is A-lista, for example. So learned variance, there's many of them. We will see them in the next slide. The idea of this learned variance is that we take hyperparameters of these schemes and we learn them through the procedure that I mentioned before. For example, in this case, the upper parameters could be the soft thresholding parameter, gamma k, and the step size psi k that we will learn. And this will be a sequence of parameters for k equal to 0 to capital K minus 1. And this will be our variable theta, which is the upper parameter of the methods that we learn. So let me show you the behavior on this scheme. So this is the fractional problem solved that I want to apply, which is literally 1 minus the expected risk. And this is the behavior that we obtain for these methods. First of all, we have 10 iterations only because we can actually show that we can solve all the problems with just 10 iterations, which is remarkable for a first order method. Then we have on the y-axis the fractional problem solved. Then here I have different variants of this scheme. I have G-lista, T-lista, A-lista, and lista. These are all learned variants. It's not super important to understand the differences. The main difference is that lista was the first one that tried to learn almost the entire mapping between one iterate and the other, so it requires lots of data to work well. And the other ones are a bit more, they add more structure, so they require less data. The dotted black line is ISTA. So what happens here is that the black line ISTA doesn't do much, cannot solve any problem within 10 iterations, which is expected because 10 iterations are very few. Lista also cannot solve any problem. It's a bit hard to see, but it's exactly overlapping with the black line here. And this is because it requires too much data to understand the structure of what's going on here. However, the other variants that learn just a few hyperparameters work very well. And the best one is G-lista, where the dotted line is the empirical auto-sample behavior, and the solid line is the actual bounds that we provide. So they're very tight, and we can guarantee that within a handful of iterations we work well. And you could also build interesting plots like the 90th quantile plots, where here I have the y-axis is the performance that I'm interested in, which is the normalized mean squared error. And here I have the number of iterations. So for example, here I tell you that in 7 iterations, I can exactly bound that that glista will solve all the problems, 90% of the problems within just 7 iterations here. And the true behavior, which is the dotted line, is slightly below that. And these results are with high confidence, which means that we can actually trust them quite well. And is confidence almost like 0.999. So this means that for these distributional problems, learning these methods provides, it's a very sensible thing to do. We can show that we can construct bounds that are very close to the empirical performance. And also we can, our bound just tell us that if we tune the methods well and the hyperparameters well, we just need 10 iterations to solve this. These are standard examples that are used in the learning to optimize literature. I'm not guaranteeing that these learning methods work for any possible schemes, but here I'm just showing you that we can reliably construct auto-sample performance guarantees for these methods, but also for learned optimizers. Okay, so now let me just conclude. So these are the references that I was talking about. So performance verification, the first paper is about the mixed integer linear programming formulation. The second one is about semi-definite programming formulation, relaxations of that problem. And then we have some of them on learning to optimize. The first one, I haven't had the chance to talk about it, but we learn worm starts for this first of the methods, and we provide generalization guarantees similar to the PAC-Bayes ones that I told you about. The second one is the one about performance guarantees using data, which is the plots that I actually showed in the numerical examples. And the last one is about which kind of hyperparameters we end up learning in these schemes after we apply stochastic gradient methods. I would like to now briefly acknowledge my great collaborators. So the people who really led this work are the ones at the top. So my graduate student Vinit Ranjan, who worked on the performance verification part, my postdoc Jisun Park, and my graduate student Rajiv Sambaria, who who graduated last year and is now a postdoc at UPenn. And then I have also collaborators Brandon from Meta, Georgina from INSEAD, Andrea from Cornell Tech, and Stefano from University of Pavia. So to conclude, what I would really like you to remember from this is that to analyze and design optimization algorithms, the parametric structure of these problems really matters. And being able to run these schemes once in a while to observe how this structure is exhibited throughout the instances is very important, and we should take that into account when both analyzing and designing these methods. Another important fact is that data can help us in two important ways. One is to design optimization algorithms, which is to learn optimizers, and this is something that people have already done quite extensively in many different ways, and of even better ways than what we were able to do. But what I would like to add on top of this is that not only we can design algorithms using data, using training schemes, but also use data to understand and verify their performance using the techniques that I showed you here. So probabilistic performance analysis of first order methods is something that can be achieved in a similar way as what's being done currently in statistical learning theory for common predictors. And then the third thing that I would like you to remember, hopefully most important one, is that we should maybe rethink how optimization algorithms are developed and deployed. So historically, people thought about solvers as a general purpose tool that solves any problems of a function class, any linear program, any quadratic program that fits the function class that I'm targeting. But maybe instead of looking at that, we should look at a more task-specific view where instead of any quadratic program or any linear program, you may be interested in just the ones that are specific to the application at hand. So then you don't care about any problem, you care about the distribution of instances that are relevant for your application. And then you can develop tighter convergence analysis and also train optimizers that do very well for that set of problems, and also be able to deploy them anywhere. Because in the sparse coding problem that I mentioned before, being able to deploy these after we guarantee that we need only 10 iterations, it means that we can deploy these systems almost anywhere, even on embedded devices that are very light computational power. And this is very similar to what people do in machine learning. You do a lots of work offline, you do validation, and then you can deploy these architectures in real time very flexibly. And I think optimization algorithms in the future, they will follow a similar type of development and deployment schemes. With that, I'd like to conclude. These are my contacts, and I'd be very happy to answer any questions.